Hey students, let me kind of expand on this number 10 from chapter 33. The problem itself is pretty straightforward, but it's got a couple, or at least one, significant subtlety in it that had a few questions at the workshop on Friday. So I thought I would expand on it here a little bit. Let me just read it here. It says a 20 millihenry inductor is connected to a standard electrical outlet. And then they, and standard North America, so the RMS voltage is 120, the frequency is 60 hertz. It says determine the energy stored in the inductor at a particular time, and this phrase is going to come important, assuming the energy is 0 at time equals to 0. Now, the simple part of this problem is that the energy, and so we called it U, in the inductor, or we even could call this U sub B for magnetic, since the inductor stores its energy in the magnetic field. And we learned that it is 1/2 Li squared. In fact, it was very similar to, I'll put here, U in the electric field was 1/2 CV squared for the capacitor. All right, so on the surface, it looks pretty straightforward. All we need to know is the current and the inductance. And the inductance is directly given. And the current, it seems pretty straightforward because it just, keeps changing with time. But here's where I guess I want to be careful with this phrase and what I did in class. See, what I did in class was this. I took an AC power source to an inductor, and I said, okay, if you do Kirchhoff's loop rule, you'll have the voltage as a function of time from our function generator, and then minus the L di dt from the voltage from the inductor, and that completes the loop. So there's only two elements in our loop, the power source, which changes with time, and then the inductor. And then, of course, the power source, as this is implying, is some maximum voltage times, and here's where I'm getting at. In class, I put sine omega t. And so if I made a graph of this, and maybe just see my axis in red, why don't I switch over? Hey, I lost my blue pen somewhere. Okay, well, let me do this black one here. But what I'm saying here is the voltage looks like this, a sine function. But the thing I want to emphasize in this video is, since it's a cycle, where we pick time equals to 0 is kind of an option for us. And in my derivation in class, I picked time equals to 0 such a way that the voltage was 0 at time equals to 0. And so it just oscillated from there. All right, I'm gonna come back to that. Let's keep working on the math here, because then we have this minus L di dt equals 0. When we move things around, we get maximum voltage sine omega t equals a positive L di dt. If we move L to the other side, and then we finally now integrate. That is, we have a separation of variables. We put everything with t on one side and integrate, and then we put everything with I on the other side and integrate. The idea here, let me just get a notepad here, call it page 2, okay. The idea being here that over here on the right side, I have the current I, and over here on the left side here, I have the maximum over L. And then when I integrate a sine, I get a negative cosine omega t over omega. And then, of course, we kind of rearranged that and kind of looked at the equation. We put the omega out in front. I left the negative with the cosine instead of bringing it in front of the equation, so that I could think of this as an amplitude. And in fact, we called this then the reactance of the inductor. And so we're saying here that if you take the maximum voltage and you divide it by the reactance, then you multiply by this trig function, you're going to get the current. And so this right here becomes then the maximum current. Okay. And of course, this oscillation being a negative cosine function, well, let me come over to here. Keep thinking I'm going to find that blue marker somewhere. Let me grab my green one here. But a negative cosine for the current, I'll do here in green, would be out of phase. And that was the main lesson, that the current and the voltage are not in phase. And actually, the other part of the lecture was that then the maximum current depended on frequency. For this problem, I won't worry about the frequency dependence of the reactance. But what's important here is this phase. And so what we noticed here is voltage and current don't reach their maximum together. This black one comes first, then the green one. And so that means the voltage leads the current. And a good way to represent that is the name Eli, because the L, representing the inductor, has the EMF leading the current. And so there's Eli. All right. Now, notice, though, that I said in this whole derivation that this depended on how you are counting time equals to 0. And back in this problem, they say, assume the energy is 0 at time equals to 0. So they're giving you a definition of when time equals to 0. And it may not be the same as what I derived in class. And so what comment I wanted to make here was, don't start this problem and say, okay, this is the equation then for the currents. It may not be a negative cosine function. It only comes out to be a negative cosine function if the voltage is a sine function. But what we do know for sure is that the EMF, the voltage, will lead the current. Okay, so when I come over here and now give that some deeper thought, if they say, go ahead and assume that the energy is 0 at time equals to 0, and since the energy has to do with current, this particular problem, if we look at the current graph, which is in green, we need it to be 0 when time is equal to 0. That's why this negative cosine function, this green one here, will not work, even though that's what I derived. So we need to, I guess, change this a little bit and make sure we adjust our axes here so that our time equals to 0 is when the current is 0. And I suppose one way of doing that is looking at this graph and saying, all right, let's put time equals to 0 right here. And so following this green one, then the current would go up to a maximum and then, back down and whatnot. Okay. So we have one, I didn't say that well. 1/60th of a second would be the period. So if I'm looking at this graph, if I'm calling this time equals to 0, a 60th of a second would be right there. Now, doubling that, I'd be at 1/20th. Doubling that, I would have its maximum at 100 or 101 over 240. And I guess I'm somewhere in between. I'm looking maybe right about there for the current. Okay? But here's what I need to do then. What I need to do is readjust this equation we worked out in class. I need to write it this way. I need to write it as maximum voltage divided by the reactance of the inductor. And now I need to write it as cosine omega t. I'm sorry, sine omega t. That's really the key. And all of my 11 minutes and 25 seconds of talking here was really just a justification of why I could take this equation in class that we had a negative cosine and just get rid of it and write it as a sine. Because a sine and a cosine are essentially the same thing. It's just when do you call time equals to 0. And my justification of changing it from a negative cosine to a sine is because their definition of 0 is different than my definition of 0. Okay? All right. So if you take that with some understanding, you could actually begin the problem right here. And then say, okay, let's find out what the current is. And you'll put in the maximum voltage. They did tell me that the RMS was 120. And of course, I emphasize that a lot in class. So I hope you catch that it was 120. If they had just said plugged in North America, you'd put 120 for the RMS. And then to make a maximum, you multiply by the square root of 2. Then I will divide by omega L. Omega, since it is 60 cycles, is that famous 377. That's worth memorizing. And the L is the 20 millihenries. And then the same thing here. We can go sine, and we can go omega, 377, and 1/80th of a second. In fact, since we're using radians, this might be nice to actually leave as 2 pi times 60 over 180. So that it becomes then 120 over 180 pi. And then dividing by 60, this is a 2/3 of a pi. And that brings me back to this little picture here, because looking at this green one, this would be pi. And so we're not quite that far, but we would be past the maximum, which is pi over 2, and we'd be here at right there, 2/3 of a pi. Okay? So if I take that 2/3 of a pi, let's see what I get here. Let me check the mode in my calculator. Yeah, let me switch over to radians. And so I will go sine 2/3 of a pi. And yeah, it should be, what, 120 degrees. So that's, yeah, root 3 over 2. Okay. So that's what this factor is. And now, if I multiply it by these other factors, so times 120 times the square root of 2, let's go inner, then divide by 377, and divide that by 20 times 10 to the negative 3, we're looking at a current here of about a 19.5 amps. And in fact, just out of curiosity, I'm kind of curious, just kind of the maximum here. This would be, the reactance would be 377 times 20 milli. So it's about 7.5 ohms for the reactance. The maximum is the standard 170. That's what, of course, we've been talking about in class, 120 times the square root of 2. So it's 170 divided by that last answer. So looks like the maximum current is about 22.5 amps. So again, coming back to our graph, it ramps on up, and in a quarter of the cycle is here at 22.5 amps. Now it has tapered off, not by much, but we're down to 19.5 amps. All right, so now we can actually finish the problem by just saying it's 1/2 Li squared. And so, if anything is challenging about this problem, it's not directly calculating the energy, it's about the current and the timing of the current, because it changes with time, and then their definition of when time equals to 0. All right, so finishing this up here, let me go and put in a 1/2 times a 20 milli times a 19.2 squared, and it looks like the energy at that particular moment, and again, I say that moment because it would change with time, would be 3.8 joules of magnetically stored energy because of the magnetic field. All right. Hope that clarifies why when you look in the solution, you will see the author just jump right to here, a sign, when in class we derived a negative cosine. All right, take care.